All right, welcome back. So we're going to extend our knowledge of solids of revolution, which essentially is a collection of tactics where we employ integrals to compute the volume of three-dimensional figures. So allowing us essentially to conceptually think of integrals as being something beyond just a computation of two-dimensional areas. Integrals can compute things broader than that. So at least taking it into three dimensions, we can talk about volumes. To recall what we looked at last time, we looked at disks, utilizing our sort of tactic of choice in this three-dimensional volume situation. Rather than imagining our entire region revolved around the axis of interest, which is a perfectly fine thing to do in some sense. I mean, you can imagine this figure sort of revolving around and taking on a three-dimensional shape. But really, to get a concrete grasp of what's going on as tangibly as possible, I think, we just take one rectangle from a Riemann sum and revolve it, because certainly it's easier to compute the volume of a rectangularized figure than it is some sort of curvaceous figure. And so, hey, we take this rectangle and we revolve it around the horizontal axis. What we get ultimately is a disk where the radius of that disk is just f of x, and the width of that disk is just delta x, and the resulting expression for the volume of this one slice, pi f of x squared delta x, can then essentially be inserted into an integral over our region of interest to compute the volume of the region precisely. And so the integral from a to b of pi f of x squared dx, replacing the delta x with dx, because when we integrate, we imagine the width of that rectangle becoming very small. So you can imagine that capital D of the delta becoming a little d down here in the differential notation. But so be it. Hey, nonetheless, this allows us to compute the volume of a figure where you take a region between one function, the horizontal axis, and revolve around the horizontal axis. What I'd like to do today is sort of extend out one step further. Instead of just considering one function above the horizontal axis, what if we consider two? So let R be the region between the graphs of f of x and g of x. On AB, we're going to find the volume of the figure that results when region R is revolved about the x-axis. So we're going to revolve here about the x-axis and, well, see what results. Now, the best way probably to get this tangibly understood is to just look at a particular x and consider a representative rectangle from the Riemann sum being revolved. And now, if you imagine this rectangle being revolved, because this rectangle does not touch the axis of rotation, there is going to be a hole in the middle when this rectangle revolves, and the resulting slice of our figure is going to have a hole in the middle. So here is one slice of volume that results. It's going to take this washer shape. Instead of a disk, the washer is essentially a disk with a hole cut out. And so, well, how do you compute the volume of this slice? Well, it's just the volume of a disk with another disk removed. So the way you might think of this is like pi big R squared minus pi little r squared times width. So when we did the pi r squared times width, we were thinking of the area along the surface area times the width. Here, the surface area is just the area of the big circle minus the area of the little one. And so if you do the pi big R squared minus the pi little r squared, hey, that makes a lot of sense, actually. We're here, just to be precise here, the little r is the small distance from the axis of rotation to our washer's perimeter, whereas the big R is the large distance from the axis of rotation to our washer's perimeter. So the washer sort of has an inner perimeter and an outer perimeter, the inner perimeter defining the circle that's removed, and the outer perimeter defining the circle from which the inner circle is removed. Right, but hey, let's start figuring out what the capital R, the little r, and the width are. Well, the width is just delta x, right? Because whenever you're looking at this disk is very thin. How thin is it? It's a delta x thin. So we can replace width with delta x. What about big R? Big R is distance from axis of rotation to top of washer. Well, the top of washer actually coincides with the top of this rectangle, if you think about it here within the context of this picture. And so big R, in our case, is just the value of f of x. The height of function f determines the value of our big R. So big R is just f of x. And then what about little r? Well, hey, little r is the distance from the axis of rotation to the bottom of the rectangle, to the inside of the washer. Well, the bottom of the rectangle here is at the height of function g. And so the little r here is actually just g of x. And so little r gets replaced by g of x. Here, let me tell you what, just to make this easier to visually parse, because there's a lot of information on this slide. Let me put that vertical line there to help visualize this, but hey, piece it all together. What's the volume of our slice? It's going to be pi f of x squared, that's the top function in this case, minus pi g of x squared times all times delta x. And so what would the volume of our region be? Now we're going to use our technique like we used previously. You just take the expression for the volume of one slice and you insert it, as cumbersome as it may be, into an integral. So the volume of our entire region will be the integral from a to b of pi f of x squared minus pi g of x squared dx. And I tell you what, since, well, you can see this expression is quite long and cumbersome, maybe I'll just factor out the pi. That's a constant multiple, right? No x is involved there. And if we factor out the pi, we just get pi f of x squared minus g of x squared. Well, let me write this more carefully. Pi g of x squared dx. But right, so here is the formula for the volume of a region between a and b that lies between functions f and g that's being revolved. Ultimately, the resulting slice is not a disk, but a washer. So be it. We can still process the computation using the methods that we described previously, which is ultimately to take one rectangle from our Riemann sum, revolve that rectangle, compute the volume of that one slice, and then insert the volume of that one slice into the expression of an integral over your region of interest. Here I just factored out the pi because why not? It's a constant multiple. But we are really cooking now at this point when considering the application of integrals to three-dimensional solids of revolution. In the next video, I'll take some time to sort of articulate some of the nuance with the washers and the disks if we start moving axes of rotation along or considering functions of y instead. But for now, hey, we are off and rolling.